Hello, and thank you for reaching out our presentation on a robust and decoupled position and stiffness control for electrically driven articulated soft robots. My name is Adriano Fagiolini, and I'm assistant professor at the University of Palermo in Italy. And this is a joint work with Salvatore Pedone, PhD student in Palermo, and Dr. Maja Trumic and Professor Kosta Jovanovic from the University of Belgrade and the School of Electrical Engineering. We have all seen the continuous shifting from rigid robots caged in order to prevent human-robot interaction to rigid robots interacting with humans and exchanging forces in order to accomplish their tasks. And we're really looking forward for having mechanisms with fully embodied elasticity. In this work, we focus on articulated soft robots with rigid links and elasticity concentrated at their joints. And we assume that actuators can change the link positions and set the internal joint stiffness. And we focus on the electrically driven ones. In this context, we want to close the loop on both position and stiffness simultaneously and in a fully decoupled way, so that an end user can independently specify the desired trajectories with these two variables. We believe that such an approach can enable in the near future faster, more dynamic, and more reactive applications with robots. The model of a soft robot with electrically driven actuation comprises a link dynamics with elastic torque acting as an input, and two agonist and antagonist motor dynamics, where the deflection vectors phi A and phi B play a fundamental role. As for stiffness, as we all know, it is defined as the partial derivative of the local elastic torque with respect to the local deflection variable. In this way, the model is overall differential and algebraic, which is the reason why common approaches close the loop on a position but control stiffness only in open loop. In developing our solution, we want to minimize also the information needed to realize the controller. As a first step, we factorize the actuation model by using functions from a basis that depends on the deflection variables, which are quite general. In this way, the elastic torque is factorized as a product of the constant matrix pi and the regressor matrix gamma, which is block diagonal and that can be systematically obtained. In this way, we obtain the formula that is the last expression in this slide. Moreover, we want to obtain a stiffness dynamics, and following the idea by De Luca and Lucibello in 1998, we consider the time derivative of stiffness, which by using the basis function reads as in the formula. As you can see, the expression depends on the deflection rates, the rate by which the deflection changes over time. And this may lead to unobservability issues and noise amplifications that is undesirable. A workaround for this problem is to step back and use the integral of stiffness, so that the derivative of the integral of stiffness, that is stiffness itself, can be factorized as a constant matrix sigma and times the very same matrix, regressor matrix gamma. In this way, we obtain the following model, factorized model. Now, in the paper, we show what is the minimum information that is really needed to obtain a controller on this system. And we show that we actually only need to know a nominal value on the inverse of the inertia matrix, m bar 2 minus 1. Analogously, we also assume that the matrices pi and sigma are also expanded in nominal plus deviation parts. By doing so, we can obtain a minimum model, that is the one that you can read in the last equations on the slide, which, however, depends on, or is affected actually, on unknown input signals. Now, these unknown input signals are not vanishing, and in fact, they're actually very rich in their content, so they may prevent the convergence and the tracking of desired trajectories for Q and S. A way to overcome this problem is to estimate these unknown quantities, where in the paper we show how to recast this problem as a linear system and how to define delayed unknown input to a server by using an output buffer, including 3 consecutive output values. In this way, we can obtain a state estimator that has this form, and most importantly, we can reconstruct the unknown input with a delay of 2 samples. The nice features of this estimator is that the matrices that are involved, E, F, and G, have specific roles, and E, for example, decides the speed of convergence of the tracking errors. Now that we can estimate omega Q and omega S, we can actually design a robust controller that allows tracking of desired trajectories. This robust control includes the feedback and feed-forward terms that depend on the error in the state, the error on the predicted state, and the compensation on the unknown inputs. And this controller can ensure global and robust bounded stability for the tracking errors. Now, the proof of the paper is the proof of the theorem is reported in the paper. We have implemented this and made experiments. And as you can see in the left two columns, we are able to simultaneously track position and stiffness signals with a 3-link robot. As you can see in the red lines, the tracking error converges to 0 nicely. Also, on the right-hand side, the rightmost column, you can see the desired and the actually executed angles for the actuators. They nicely behave, so they are not producing wearing for the actuators over time. Finally, we have shown that our method is also robust to the choice of the nominal values. Basically, even the choice of the nominal value can be quite arbitrary, and while the accuracy of the method is not affected. So that's all on my side. I want to thank you on behalf of myself and the other authors. I hope you find it interesting, and I want to thank you for your attention. Goodbye.